Welcome back. So, we were discussing about the sintering module. So, in the last class we have discussed about the effect of sintering temperature, which is one of the dominant parameter for driving the sintering kinetics for for any of the material, be it metal or ceramic or even metal or ceramic matrix composite. So, in this class we will discuss about the other sintering process variables. So, the second in line is the sintering time. So, although the degree of sintering increases with increasing time, the effect is small in comparison to the temperature dependence. So, the loss of driving force with increasing time at any temperature is one of the reasons why it is so very difficult to remove all porosity by sintering. An attempt should be made to achieve the desired properties of the sintered parts by shortening the sintering times and correspondingly achieve going higher temperatures. However, the maintenance costs and energy consumption of a furnace increase when its operating temperature is raised. So that is what I mean. We need to deal about multiple situations here. So, I can start with the drawing a sintering cycle, although I have drawn earlier, but I am drawing again for your ease of understanding. So, assume that, so this is basically say it is a typical example of say alumina. So, where the sintering temperature is generally considered as 1600 degree centigrade. So, here this is a interesting concept to understand. So, so as we increase the sintering time, so up to a certain extent we see the increase in sintered density, but beyond that sintering a particular time, if we increase the sintering time further, then we will experience grain coarsening. So, and as well as we can see pore coarsening, because there is not much change in in the density of the sintered part further beyond a trade off time. So, assume that this is a time of say maybe 150 minutes, that is considered the optimum one. So, this is a matter of optimization where we need to check based on the maybe the mechanical property and the physical property of the sintered part at different time intervals, because this is again dependent on the powder particle size. So, particle size. So, like so that in case of smaller powder particle size, we can see that surface area will be much higher. So, we can basically achieve faster sintering kinetics, and we can even accomplish the sintering at a lower sintering temperature, whereas in case of coarser powder particles we need to go for higher sintering temperature. So, so if the particle size is constant, in that case beyond a particular optimum sintering time, then we can experience grain coarsening as well as we can experience pore coarsening. So, these are the two things we can experience with the if we go for a prolonged sintering time. So, so that is why it is very much important to optimize the sintering time, and simultaneously like if we try to decrease the sintering time by increasing the temperature, then it also pushes the equipment to the limit, because higher temperature means that it needs to use higher energy source, and that may not be economical at all. So, that is why there, and also if we are trying to decrease the temperature to save on the energy resources, and then we are increasing the sintering time, then again it is it becomes time inefficient, and in that way also it can cause the production delay and the losses. So, hence so we need to come up with a appropriate time temperature combination for the particular material and also the particular part under development. So, based on these requirements we need to optimize that, and so the third variant is the rate. So, the heating rate, that is the dT/dt. So, that largely depends on the it depends on the equipment and also the temperature material in hand, because if you if the rate is increased beyond a limit, then it may not allow the densification to get started. Uniform densification rate may not be achieved at different cross section of the powder compact which is undergoing sintering. So, hence that should be controlled to a certain limit, and then other than these three, that is sintering temperature, temperature, heating rate and sintering time, it is the sintering environment. So, the proper production, use and control of sintering atmospheres which are essential for the optimum use of the powder metallurgy process. So, atmosphere is also important. So, like for example, again if I am taking the example of alumina. So, in this case we can basically achieve like transparency or translucency in the sintered alumina, alpha alumina part. So these are the optical properties that largely depends on the the environment at which this is getting sintered. So, hence the environment has a dominant role to play to decide on the physical and also in cases mechanical properties of the part being sintered. So, so this is the graphical representation. So, you can see that with increasing temperature, so T2 greater than T1, next size increases, T2 greater than T1, surface area reduction, that is delta S by S0, that ratio increases, shrinkage increases. Why shrinkage increases? Because densification increases. So, they are analogous, and then densification of course, with higher sintering temperature for a given green density we see higher densification. So, from this the effect of sintering temperature, time and the environment is quite clear. So, the material variables. So, we have talked about process variables until now. Let us focus on the material variables now, because they also play a pivotal role in determining the success of sintering process. So, the particle size, so in terms of the basic stages of sintering, decreasing particle size leads to increased sintering, higher sintering rate. So, the smaller particle size has a greater pore solid interfacial area, as I was telling you earlier. It produces a greater driving force for sintering, and it promotes all types of diffusion transport, that is greater surface area leads to more surface diffusion, and small grain size promotes grain boundary diffusion and a larger interparticle contact area to volume diffusion. So, this is the effect of particle size, and then next is the particle shape. So, the factors that lead to greater intimate contact between particles and increased internal surface area promote sintering. So, so these factors include decreasing sphericity and increasing macro or micro surface roughness. So, this is the effect of particle shape. So that is what I mean. So, that is why we if you recall that we have discussed earlier about the the necessity of achieving spheroidal powder particles, and if in spite of that if we get the irregular powder particles. So, like this, so we can achieve the greater interlocking during green compact preparation, and thereby we can achieve higher green density, but during sintering, the sintering because the connection is not that not good like we can achieve in case of spheroidal powder particles. So, that is why the densification rate is lesser in case of sintering. So, because surface area in contact will be lesser, and hence the sintered density will be lesser even if the green density is higher in case of irregular powder particles. So, so that is why you can understand the effect of powder particles shape. So, we have discussed about size, shape, then the particle structure. So, a fine grained structure within the original particles can promote sintering because of its favorable effect on several material transport mechanisms. So, the transport mechanisms we have already discussed, take GB transport, lattice diffusion, diffusion from the dislocation. So, with a finer powder particles, grain size within the powder particles. So, in that case there is every chance that we can also achieve the fine grain morphology in case of the sintered part also, densified part also, and also fine grain morphology, presence of fine grain morphology in the powder particles can effectively promote the sintering densification process, and so because of the favorable effect on the material transport mechanisms. So, number 4 is particle composition. So, alloying additions or impurities within a metal can affect the sintering kinetics. So, so the effect can either be deleterious or beneficial depending upon the distribution and reaction of the impurity. So, like we can also often we add grain growth inhibitors. So, these are like dopants. So basically, for example, like magnesium oxide, MgO, ZNO, these are quite famous as grain growth inhibitors. So, they what is their role? They are basically not letting the, so they basically do the pinning effect at the grain boundaries, and they do not let the grains to grow beyond a certain limit, and that in that way we can achieve fine grain morphology. And as we know from the Hall patch equation that we can basically achieve, which is nothing but sigma is equal to k d to the power minus half. So, from here we know that if our d, that is grain size, is less, that is finer, we can achieve higher strength in the sintered part. So, that is why the role of particle composition plays, and also other than using the dopants or the grain growth inhibitors, we can also like we can achieve liquid phase sintering, as we have discussed in the former class, that which are can be added with the powder particles during compaction stage, and that can basically form the liquid pool that is needed during sintering, and which can basically promote the diffusion and mass transport between the neighboring powder particles, and thereby can be effective to the densification mechanism. So, so the reaction between impurities and either the base metal or alloying additions at the relatively high sintering temperature may be undesirable. So, then number 5 is green density. So, a decreasing green density signifies an increasing amount of interfacial surface area, internal surface area, and consequently a greater driving force for sintering. So, although the percentage change in density increases with decreasing green density, the absolute value of the sintered density remain highest for the highest green density material. So, this thing is very important to understand. So, what this statement means? So, this statement means, even if I go back to the example of the previous example, like when the but you cannot compare this when your particle sizes are different. When assume that if you have a powder aggregate or consisting of both spherical powders, and in one case you have a lesser green density, that means say GR green density for a material A is less than the green density of material B. So, then as I have told you earlier, when the sintering temperature and the sintering time and the powder particle shape and size are constant, then we will end up getting higher sintered density, like ds A will be lesser than the sintered density of the material B, but the sintering rate, that is the so the rate of sintering, so we can define it as say dx dt, rate of sintering. So, rate of sintering in case of material A will be higher than the rate of sintering in case of material B, but however, it will never be able to match the density of the material B, because it is having a higher green density when all other sintering process conditions are kept constant. So, this is important to understand. So, hence it is, although the sintering can be faster, but to achieve the higher sintered density, we suppose we are expected to start with the higher green density, as much higher green density as possible. Okay. So, we going ahead with the theory of sintering. So, the dimensional changes that happens in the sintered specimen. So, changes in dimension resulting from sintering represent an important field in powder metallurgy, especially with respect to large scale production of parts with small dimensional tolerance. So, the fundamental process of sintering leads to a reduction in volume because of pore shrinkage and elimination. So, following factors in this regard may be considered. So, number 1 is entrapped gases. So, the expansion of gas in close porosity has been postulated as producing compact expansion. Number 2 is chemical reaction. So, hydrogen is a common component of sintering environment, sintering atmospheres, and can often diffuse through the metal to isolated portions of the compact, where it reacts with oxygen to form water vapor. So, the pressure of water vapor can lead to expansion of the entire mass. So, it is also possible to have reactions that lead to the loss of some element from the sinter mass to the environment, such as volatilizing and result in a shrinkage of the material. So, I mean, so this is about, I mean, the effect of entrapped gases between the in the close porosity, and also the effect of chemical reaction what hydrogen can cause when it can react with the oxygen and cause water vapor formation. So, so that is the another effect that can cause dimensional changes. However, the sintering associated densification happens in the powder aggregate that negate the effect of the increase in the volume due to the these chemical reactions and even because of the entrapped gases. So, so the net dimensional change we often see negative, that means that is the shrinkage because of the densification rate predominates the effect of the gas entrapment or chemical reactions. And then the third is alloying. So, alloying that may take place between two or more elemental powders very often leads to compact expansion. So, this effect, which is due to the formation of a solid solution, is often offset by shrinkage of the original porosity. Okay. So, the shape changes. So, effect of green density variations. So, variations in green density in complicated compacted parts significantly affect shrinkage during sintering. So, with low density regions showing more shrinkage. So, that is quite natural, because low density means the presence of powder the additives or the polymers is higher, that is why it is having lower density in case of whenever we are adding the additives, and that is why during sintering during debinding stage, these are the locations from where higher amount of binder removal will take place, which results in higher percentage porosity, and then higher porosity means lesser green density and higher driving force for sintering. So, sintering becomes faster, and also the because of that we can also experience higher shrinkage in the in those locations. So, if you recall that we have also discussed about the essence of pressing from both the directions to avoid getting a density gradient, so that we can achieve uniform density, otherwise it may cause post sintering, because if we can achieve higher densities up to a certain thickness because of the presses, if even if in case of double acting. So, there are some corners which can be left behind, and then during sintering it can achieve this shape. So, it can achieve this this dog bone kind of a shape. Because of the weak regions where there is lesser green density. So, there it can experience higher shrinkage, and then it can lead to this kind of shape in case of double end compacted press. So, when we are compacting from both the sides, and when we are compacting only from one side. So, that case also you can just see the shape which is a tapered nature because of the density gradient, that is immediately beneath the press having higher green density, and as you are further apart from the point of application of the pressure, the density the green density is lesser, and that results in enhancing the sintering kinetics in those locations, which results in a higher shrinkage in those locations, and then it can cause a structure which is a which is highly distorted. So, so these are basically the shape changes. So, it is the effect of green density variation, shape changes during sintering. So, that is because again connected with the effect of green density, that is explained over here, and directional shrinkage. So, this is happens, shrinkage or expansion can differ between axial and radial directions and must be considered when designing and compacting tools. So, this is a important criteria. So, this is so that is why we cannot often we may not be able to apply a uniform shrinkage to all the dimensions present in the in the part to be developed via the the powder metallurgy route, and then we have to consider directional shrinkage, and but moreover this directional shrinkage also varies with the particular powder metallurgy route that is considered for developing the green compact, the preform, because based on the technique of the compaction route, whether it is loose powder or tap powder sintering, or it is injection molding, or maybe it is cold or hot isostatic pressing, the the content of the powder significantly varies in the powder aggregate. Of course, every cases there is some amount of additive present, but the content additive content differs greatly, and that is why directional shrinkage also is can be different. So, based on the material and based on the process and the dimensional requirements of the part, we need to decide on the directional shrinkage aspects, and then complex and asymmetric shapes. So, uneven shrinkage occurs in parts with complex or asymmetrical shapes, leading to loss of dimensional tolerances. So, so that is again true. So, the because complex or asymmetrical shapes can cause lack of uniform transfer of the pressure during compaction at all the locations, and that can of course cause density gradient. So, because of the similar reasons that expressed at the top, it can also cause variational shrinkage and analogous loss of dimensional tolerances. So, tolerance restoration. So, sizing operations are commonly used post sintering to restore tolerances and correct uneven shrinkage effects. So, this is how it can be corrected. And the microstructural changes. So, when a green compact is sintered, the original particle boundaries can no longer be observed. So, instead the structure becomes similar to that the metal in wrought and annealed conditions generally demonstrate. So, only difference is that in case of powder metallurgy part, it generally contains pores trapped at the grain boundary triple points as a closed isolated porosity. So, the pores are of two types, open or closed. So, with progression of sintering, pores continue to shrink. So, at about 5% of the total porosity, the 5% total porosity left, the formation of closed pores commences. So, many of the microstructures seen in PM parts are caused by porosity and by the blends of elemental powders that constitute many alloys. So, these blends do not always result in homogeneous well diffused structures. So, such heterogeneity is not necessarily detrimental, and in certain nickel steels and diffusion alloy steels may be advantageous. So, so that is why the microstructure of course can be bimodal, and this microstructure can be bimodal in case of alloyed powder alloying, where there is in situ alloying takes place. Solid solution formation happens during sintering, because when we are mixing one or two powders together to consolidate and then finally sintering, and also in those cases the the kind of porosity it evolves because of the presence of two phase microstructure is also different, because of the different densification rate of the analogous the powder particles that are mixed for for in situ alloying. So, the such heterogeneity, these blends these blends do not always result in homogeneous well diffused structures. So, such heterogeneity is not necessarily detrimental, and in certain nickel alloy and diffusion nickel steels and diffusion alloy steels may be advantageous. So, it can be preferred also at times. So, the heating or annealing of cold work metals leading to three distinct microstructural changes, that is recovery, recrystallization and grain growth. So, that is quite intrinsic, like when we are talking about sintered parts also the similar mechanism takes place. If we are processing the sintered parts by annealing post after cold working, if we go for heating or annealing. So, we can observe the similar mechanisms in case of powder metallurgy processed materials or alloys also. Okay. So, coming to the sintering temperature. So, sintering atmosphere and metal interaction. So, metals react with the surrounding gases, especially at higher temperatures. So, the primary purpose of sintering atmospheres is to prevent oxidation and reoxidation. So, gases may enter pores, get trapped, like we have discussed earlier, gas entrapment, chemical reaction. So, these are the possible effects that can happen because of the environment, the gases present in the sintering chamber. So, hence of course, if we are not desiring to these chemical reactions, then we generally use the gas cover as an inert environment to avoid oxidation, unless there is some special reason for achieving reactions in situ during sintering, which is not the case in most of the occasions. So, in hydrogen. So, hydrogen is a commonly used reducing gas due to its excellent properties. It is economical only for high value products and highly flammable with a short hot flame upon contact with the air. So, reformed hydrocarbon gases. So, cost effective gas mixtures are classified into exothermic gas and endothermic gas. So, in exothermic gas produced by incomplete combustion of fuel gas and air in refractory lined water jacketed generators operating at 1100 to 1425 degree centigrade. So, and then temperature depends on the air to fuel gas ratio, gas volume and heat transfer efficiency. So, this is the case of exothermic gas. So, this can also be used as a sintering environment at times. The other case is endothermic gas. So, formed with a lower air to gas ratio requiring external heat. So, they do not generate heat, it is basically the heat is needed for these cases, these gases. So, rich in carbon monoxide, hydrogen and methane, making it strongly reducing and carburizing. So, when we are needing the carburizing environment, when we are also expected to do the surface carburization of the part which is being developed via sintering route, then we can of course go for endothermic gas mixtures as sintering environment. So, controlled composition ensures equilibrium with the carbon potential of the steel. So, so factors affecting endothermic gas. So, the exothermic gas generator is a refractory lined water jacketed combustion chamber that operates at 1100 to 1425 degree centigrade. So, the internal temperature of the chamber depends on temperature in the cracking zone, air to gas ratio, catalyst efficiency, residence time in the cracking unit. The cracker temperature must match the sintering furnace to avoid instability, soothing or uneven sintered properties. So, this is the role of the sintering environment. And so, if, this slide basically summarizes the effect of powder processing with pressure. So, we are so in case of so aggregate is almost instantaneously consolidated to high density by plastic deformation in case of pressure assisted processing. So, no further closure of pores is possible by plastic collapse as the external pressure reaches equilibrium with initially internally developed stresses. So, so the extent extent of densification is dependent of the applied pressure. It is possible to attain densities as high as 95%. A time dependent deformation driven by effective stress, sigma effective and temperature. So, various creep mechanisms gets operative. So, so this is the if you compare that pressure assisted sintering and sequential compaction and then sintering. So, in this case these are basically done sequentially one after the other, and so like when we are doing the compaction, generally we do it at a much lesser temperature, if not room temperature, then it is of course at a temperature when only the additive or the polymeric ingredient remains in the liquid state, but not the we never nowhere go closer to the I mean even sintering temperature of the powder aggregate, that is basically undergoing sintering. So, the role of applying pressure is just to achieve a higher grain density in the powder compact in case of traditional PM processes. So, then the pressurization phase is followed by the I mean thermal heating stage in this case in traditional cycle, and in case of full density cycle when we do a combined pressure temperature pressure and temperature assisted process together. So, then we basically get a additive effect between temperature and pressure. So, in this case we apply the sintering happens at the onset of the applied pressure. So, hence we also achieve higher sinter density. In this case, what are the examples? Example of this technique is a HIP, that is hot isostatic pressing, where the pressurization and the heating stage are combined to each other. Okay. So, in case of sintering, a time dependent deformation driven by effective stress sigma effective and temperature T. So, in this case various creep mechanisms gets operational. So, higher stresses, dislocation creep, increasing pore closure, so stress becomes low and diffusion more prominent. So, then with the increased curvature of pore surfaces, so diffusion becomes more prominent. So, effective stress present in the material due to the externally applied pressure causes local strain. So, the net effect of local strains combine to give overall contraction of the sample undergoing sintering, that is also called as a whole as densification. So, the effective pressure P effective is equal to sigma effective is equal to 3 by 2 P theta ln theta by 1 minus theta. So, then where P is the applied pressure and theta is the porosity. So, expression for first stage that is plastic collapse applied pressure. So, in this case P is equal to 2 by 3 sigma 0 theta, sigma 0 is the overall stress minus 4 by 3 sigma 0 minus sigma y, that is overall stress minus yield stress of the material ln epsilon. So, ln is the basically strain. So, here epsilon is equal to root over 1 minus theta, that is the theta is the initial porosity, theta 0 theta is the porosity after post the processing, and theta 0 is the initial value of the porosity. That means porosity of the green compact. So, then this is the expression where from we can calculate the strain value, and we can also calculate the the pressure needed. So, from the sintering stress that is getting generated, that is sigma 0. So, this is high. So, at any point P is equal to 2/3 sigma y ln theta. So, plastic collapse stops when the pressure reduces below the critical value. So, so this is how we can determine the pressure needed so for pressure assisted sintering processes. So, where it is some simultaneous effect of temperature and pressure can be seen. So, expression for second stage of densification. So, time dependent deformation driven by effective stress sigma effective bar and temperature T. So, for power law creep processes, net creep rate can be approximated to the sum of the individual creep rates. So, this is epsilon degree is equal to total creep rate is equal to summation of AI sigma effective to the power Ni. So, where Ni A and Ai are the creep constant for a particular mechanism at this stage of densification. The second stage, that is the thermally activated stage, where the pressurization stage is done, and we already discussed about the pressurization stage earlier. The mechanism prevails at that stage. So, the second stage, which is a thermally activated stage, where we generally do not apply pressure. So, we are talking about the traditional process here, traditional sintering process, where the pressurization and the thermally activated stages are separated as and sequential, that means one gets activated after the other one. So, we are talking about the conventional techniques. So, in this case so at this stage of densification, overall densification degree theta is related to porosity, overall strain rate due to creep is degree theta is equal to epsilon x 0, epsilon y 0 and epsilon z 0 into 1 minus theta. So, strain rates in the three mutually perpendicular directions over the component as a whole is shown over here. So, that is why overall strain rate is named here. And then the rate of densification during diffusion creep. So, the by Koble given at 1970, and the rate of densification during entire sequence of pressure sintering given by Wilkinson and Ashby 1975. So, here the expression can be written like this. So, theta dot is equal to k theta by 1 minus theta to the power n a p to the power n, where a and n are material constant. So, this is basically the case when strain rates so pressure assisted sintering, it is a different expression that we can get compared to what we can get in case of sintering process, where we do the pressurization stage and the thermally activated stage separately. So, with this we are stopping here for this class today, and we will continue with the mechanisms of sintering in the subsequent classes. So, thank you till then.